Hi everyone. I want to talk about a project that I've been working on. Specifically, I have a 3-node Raspberry Pi cluster that I am wanting to install Kubernetes to it as part of my journey to being certified with as a Kubernetes administrator. And as part of that effort, I have been kind of playing around with virtual machines, and then I'm like, well, I want to test in real hardware, but I don't want like a big giant or a big set of clusters or nodes in my closet. So I opted to go with a Raspberry Pi cluster. And so here on the screen, uh, I'm going to kind of walk through the project and what I've done so far. I will not cover the actual Kubernetes portion of it. Pretty much what I will cover is the the Raspberry Pis themselves. So from assembly to um, image patching to actual Bootstrap orchestration, uh, flashing the storage, until we actually get a running system. I will also be covering some network configuration um, choices that I made, and I'll show everything. So on the left here, I have this markdown document that I'm showing, which is kind of my like overall agenda that I'll be going over. So here, as I mentioned, kind of what I'm showing here is kind of like a diagram going over kind of the series of steps of what's done, right? So as part of this bootstrapping process, I chose to go with Debian OS, so Debian 13 Trixie, which is the latest stable version. And the reason why I chose Debian Trixie is one, it's the latest, and two, it's an actual smaller image than Ubuntu. Originally, when I actually tried to do all of this, I went with Ubuntu 24.04, but the the resource utilization for Ubuntu was actually higher in comparison to Debian 13. So I opted to just go with Debian 13. Less things running, less things installed, meaning less of a landscape where you can get hacked and whatnot. So my thought process is, okay, what can we run that's maybe slightly low, slightly less complex, a little less surface area for attackers, and that's similar to what's being run and executed in the CKAXAM. So that's what you do. So basically, I just did a wget to download the image, which I just showed down here on the right. After I downloaded the image, you'll see here's the image that I downloaded. Actually, it's right here. It's a compressed one. And then I have this shell script called bake.sh, which will decompress it. Actually, I go through it a little bit later, so um, we'll skip over it for the time being. But I have this shell script that does some massaging of that script and patching. Then after I patch the image, I have an NVMe drive, and for all three of the Raspberry nodes, and I have this nifty little NVMe to USB basically like enclosure. So you just put it in here, and then you close it, connect it via USB-C to my desktop. From there, I just run like a straight up DD command, which is pretty much this one right here. You'll see on screen here in the bottom right. So it's just DD, and then you pass in the input file, which is the patched image that was massaged in the prior step, and then the output file, which is the device. In this case, it's in SDA for my system. But that's pretty much it. I mean, there's a little bit more to it, but you run a sync and whatnot. But anyways, after you flash the device, then you mount it. After mounting, you copy over the cloud-init files. I'll cover that in a little bit later. Then you unmount it, and then after that, you have to essentially assemble the Raspberry Pi devices, which I have some pictures I can share on that. And then after you assemble it and you connect the Raspberry Pis, assuming that cloud-init works and whatnot, and it goes through into the process. And also this kind of this document doesn't cover the network configuration, or sorry, this diagram doesn't cover the network configuration. And so actually I should just probably change that right now, because before we won't even be talking about kubeadm. So we'll just say network configuration. And then so we mount it, network configuration for both on the switch. Oh, that's why I have on the top right here my browser open, because I'll go over that in a bit. It's a little bit more than just the switch, but we'll go into more detail later. Then after networking is configured for on the switch and my host, then I power on the obviously I assemble the device, connect the NVMe drive, and then power it on. And after the first boot and cloud-init finishes, then I can SSH into the device and verifies a few things. That's pretty much kind of summary of the process and in a diagram form. And then here's kind of a list of things. So hardware wise, so I have my router is a UniFi Cloud Gateway Fiber, and then from the UniFi Cloud Gateway Fiber, I actually have a secondary switch in between, but that's not really relevant to the story here. There's another like UniFi switch that I have here, the like 24 HD, but that's kind of not, that's irrelevant here. It's just in the middle. It's just because from the gateway fiber, it's my network closet, but from the fiber it connects to that, and then from there that shoots to my office. And so here's the UniFi switch 24 port, and this is the older version that actually has still the fans inside. So not the newer versions that where they eliminated them. And then I have my Ubuntu 24.04 host desktop, which I'm using to communicate with the Raspberry Pis via SSH. Then I have the 3 Raspberry Pis themselves, 3 NVMe drives, and then the enclosure that we talked about earlier. 2 things I didn't mention in this list, but all 3 of the Raspberry Pis have the heatsink with the integrated fan. They all do. And I have this like geekdom or metal kind of enclosure for all 3 of them. So, and you'll see that a little bit later in the pictures that I have, but just I wanted to call it out. It's not listed here, but it's not just a straight up like Raspberry Pis that I have them there sitting on my desk. No, they are in enclosures. All right, so let's move on to the actual patching of the OS. So the patching of the OS, basically I have this bake.sh script. It takes a stock Raspberry Pi OS Trixie Lite image, and then it produces a ready to flash patched image. It accepts both a image and an image XZ file as inputs, and always works on a copy. So the original that I downloaded gets preserved. It will essentially This is how you run it, basically, like that. But what it does is it decompresses first the compressed file that you downloaded it, and then the original never gets modified. Then it mounts the image via loop device on my host, like the Debian host that I'm on. Then it modifies the command line txt to enable a few cgroup permissions, which I'll be using that for Kubernetes in a future session. It modifies config.txt for the NVMe throughput to get the full throughput on it, to set the PCIe Gen 3 lane. We disable swap. The Raspberry Pis, it's not like a one-to-one kind of apples to apples comparison between like a regular x86 x86 64 MD64 device, like my like my desktop. So like what I discovered is that it has some sort of a swap thing there, but all I'm trying to say is that I'm disabling it. I do not want swap enabled because I won't be using it. In fact, Kubernetes doesn't want you to have that there. So that's what I do. Then I have within my script, it creates placeholders for the cloud-init metadata, user data, and network config to the boot partition. This is in case, I were to patch, or I would flash the image onto an NVMe drive or something like that without like supplying later the actual 3 cloud-init files. After that, I chroot the image so that then I can do some minor configuration. So like I'll do an apt-get update, and then I'll like install all like my dependent packages that I want on the node itself, and then I'll do some cleanup at the end so that the image doesn't get ballooned up. Then I mount things, and then it produces that patched image. Okay, so that's pretty much what the patching of the OS bake.sh script does. Then the next step is the actual orchestration itself. So how do we orchestrate it, should I say, or precede it? So there is a per node configuration. So I have 3 Raspberry Pis, right? Each node has its own host name and its own IP address. So for like the node 1, right, of the Raspberry Pi node, in the metadata file, you'll have the host name or the instance ID set to the same value as the host name, as well as the local host name. Within the network config, I am defaulting the address to 192.168.200.10, and that is actually a 200 VLAN ID. I'll cover that in a bit later. So that's a separate VLAN network isolated area that I created on my router. In the user data, here I set the host name, set the keyboard layout. That was actually an issue I hit, where on initial setup via cloud-init, it would default to Great Britain, the keyboard layout. So I had to figure that one out, how to automatically set the keyboard to US layout, because I'm in the US, right? Then there are some kernel parameters to set that are basically used for the for when I work on Kubernetes. I'm not there yet, but this is just like kind of precede steps, so I don't have to do it later. It's all set up on all the Raspberry Pi nodes. This is for swap to disable it. So basically just creates an empty file and loading some kernel modules, the overlay and the brnet filter. We create an admin user with no password, and it does have sudo access. It can only be access via an SSH key. And in fact, in the bake.sh script, I even disable the root SSH to it, so you can't even you have the only way the entry point into the cluster is via SSH using this admin user. That's the only way. You cannot SSH to the device via root. That happens in the bake.sh script. Then after that, there were some issues that I hit with Raspberry Pis, and full disclosure, I use AI, but essentially, in working with my AI service, basically what happens is when you do a cloud-init on a Raspberry Pi, because it doesn't have a real-time clock, it has no way to kind of like synchronize it. So what ends up happening is when you do an apt-get update, the clock itself is out of sync, so it cannot verify that the app source that you're trying to pull from is valid. And so if you read up, it's not here, but it might actually be in here. So I have this note here on the actual original file that we don't intentionally use the package update and package upgrade from cloud-init on Raspberry Pis because of the real-time clock limitation. So you can like work around that, and the way that you work around that is in the run command section, you actually have to sync the clock first and the time on the device before you can attempt to do anything with like apt-get. So that's why I have kind of this like somewhat hack, if you will, to sync the time on the device, and then after that, you'll see I'll do some maintenance, right? So I will do an upgrade, make sure all the packages are upgraded on the device, and then I'll enable the Crony service, enable the SSH service, start it, turn off swap, make sure swap is not an FS tab. Just basically like do some basic steps to make sure that my cluster is working. My Raspberry Pis are working, right? After it does all of this, it will do a reboot of the system, so that everything is reproducible. So when the node reboots, I should be able to see like the kerning tunnel parameters being set without me manually doing any sort of intervention, right? So basically, we install the OS, we do some pre-setup network configuration, which is done via the network config file we showed earlier, host name, whatnot, install some stuff, and then restart the node. Okay, so that's pretty much it. Here's kind of a table mapping of the so each of the Raspberry Pi nodes. So this is the host name, instance ID, and then the IP address that I assigned to it. They're not actually static assignments in the router itself, and that's okay, because the VLAN that I created doesn't even have a DHCP server. We'll cover that in a bit, but so what I set in the network config for each of the devices, when I copy them over, and I'll get to that part in a bit, but this is what basically defines and sets the networking for each of the Raspberry Pi. So I would flash one, mount it, copy over the cloud-init files, but before I copied them, I would make sure to modify the specific information like the host names and the IP address, copy them over and unmount. So that's how I would do the initial kind of one-time bootstrap per node. Is there a better way to do this? Probably there is, but I'm not really looking to go that deep right now in that terms of automation. My focus currently is to kind of spend more time in the kind of CKA area and practice a little bit more with Kubernetes before I take my exam. So this is just the initial bootstrapping of the cluster. Now this is how I prepared the storage. So I would get the list the block device to get the name. In this case, it's dev SDA. Then I would DD the patched image that I got created before, sync the device. This is how I would copy over the cloud-init files that we talked about earlier. So I would essentially be in this current working directory that I'm showing the bottom right. I would mount first. I would create the kind of the temporary mounting directory where I want to mount the SDA1 partition, and then I would copy over the cloud-init files, all three of them, and then unmount it. Now let's talk about the assembly. So here's basically one Raspberry Pi node, right? You have the Raspberry Pi in the center right here. The right here, this is the heatsink plus the fan that's integrated. That's the NVMe drive, and this isn't necessarily a Pi hat. This is more like it allows the Raspberry Pi to be able to leverage an NVMe drive via this kind of ribbon cable you see right here. And then these are just some assembly screws and whatnot. Here's a kind of a picture of more of the original packaging and setup that I have. And then kind of a picture of, okay, here's the Raspberry Pi by itself. Here's the Raspberry Pi assembled with the heatsink, the NVMe drive, and the daughter board that's connected to the Raspberry Pi to give it the functionality for, like to support NVMe, right? And then you have the fully assembled case with the Raspberry Pi, everything in the case. Okay, so now let's talk about networking, and before we go a little bit deep into like how I did things. And so I just noticed something. Let me see if I can fix this. Because Obsidian isn't rendering this properly. And I want it to render properly so people can understand, my viewers can understand what it is that I'm trying to show. All right. Here's a better picture, or a better view of the networking kind of topology. So let's kind of explain this diagram so people understand what's happening. Okay, I have the UniFi Cloud Gateway Fiber, which is this box right here, and this is the gateway IP that's configured on it for this subnet. So we got the 192.168.200.1, and the VLAN is 200 on the gateway. In between there is kind of a, like I said, another switch here, but that's kind of hidden. It's not that important. But there's the US switch 24 that I have, and from here, this is where kind of all the devices are connected, including both the Raspberry Pi cluster itself and the Ubuntu host themselves. So on top right here, this host machine is my Ubuntu 24.04 desktop cluster, which I'm actually recording on right now. And on that device, it has actually has 5 NIC ports. It has the one dedicated on the motherboard plus a quad port PCIe card, and on that one, on that card, that quad port card, one of the devices, one of the NIC ports is configured for the specifically dedicated for that network area. And then from there, that's where I create the lab pi trunk port profile, which allows access to the VLAN from the host. And then on the the Raspberry Pis themselves, each of them, they only have one network port with their dedicated IP address that I have assigned for them. This uses a different port profile, and I'll go a little bit of detail what that means here in just a second. But so that's so you can understand that this is in its own VLAN, and the only way to be able to get access to the devices is by applying a port profile to the individual ports on the switches. So so from the UniFi Cloud Gateway Fiber console, I go and create a network. Okay, so let's go and show that. Here I'll go to settings, and then from settings, here in the network section, there I have many different networks at home. This is my basically essentially my playground here. But I've created this Lab Pi network here, and this one here, if I click on it, you'll see this is the definition of this network that I call Lab Pi. And in here, this is the IPv address, the net mask, the gateway IP, the kind of default, and then the range, starting from .1 to 254. Now, this network that I've created is isolated, meaning that if I hover over here, it basically says the isolates the network from all other virtual networks using firewall rules on the UniFi gateway. Devices on the network are able to communicate with each other. Devices on this network, so the network that I've defined, meaning that if all these other networks that I have, so lab VMs, cameras, management, default, they cannot talk to it. It's isolated fully. So the only way that they would be able to talk to each other is if a device within that network also has a dedicated an interface that has access to that network. And we'll get to that in a minute here, but there is no DHCP for this DHCP server for this network, and that's on purpose. I do not want DHCP service. All right, so once you create the network for the Lab Pis, right? You have to create two port profiles. So the access one is this one right here, right? So this one, the way this one works is on the core settings, the native VLAN network, you set it to Lab Pi and you block everything else. So basically, this basically just only gives you access within that VLAN. That's it, nothing else. Obviously, you have public access. But you cannot talk to anything else, right? So that everything in here is assigned to that. Now, so you might be asking, okay, well, how is my desktop, that I'm recording on, how does it get access? So the way that I did this is used, with the help of AI, is basically I create this secondary port profile, and in this secondary port profile, this has, I have to click on it, by the way. This is trunk. Sorry, trunk is the one I need to talk about. So access is the first one I mentioned, and then the second one is trunk. So from trunk, basically the native VLAN network is default 1. Okay, so that's the main LAN network. From there, I want to provide access to the Lab Pi VLAN 200. I actually had a little bit of trouble with this where I couldn't figure out how to set the actual VLAN ID, so I had to like play around here and click on custom, and eventually, okay, that's how you do it. So that's essentially what allows me to get access from my my desktop to the devices within that network. Okay. Now, after you've created the two port profiles that I just mentioned, right? So the network creation, the port profile, the next thing you have to do is physically you have to find out where the devices, what ports they're connected to on the switch. So like I have the three Raspberry Pis, right? And then I have the actual desktop itself, right? So that means I need to find 4 devices. So in UniFi Cloud Gateway, there's a way to go to port insights, and then from there you select your device. So we have the US switch, the UniFi switch 24 port that I mentioned, right? And then from there, you basically just go in and find your devices. So I know what my desktop port is. So my desktop on the quad port is connected on port 2 on the switch. Okay, it's actually port I think 0 on the actual quad port itself, but on the switch it's connected to port 2. And the good thing or the nifty thing here is that you can actually see, so this is actually the actual switch, the switch represented. And so like you got port 1, 2, 3, 4, so odds on top, evens on bottom. So that's how you can kind of, trace the cable back from my desktop quad port card NIC, and then from there it's connected to the switch. So I know it's on port 2. So from there, what I had to do was I had to assign this port profile. So you click on, by default this is disabled, so you have to like click on that, and then from there you can select the port profile that I created before. In this case, this is for the desktop. So the desktop needs to use the trunk one, because that's the one that allows from the default LAN network access into the VLAN 200 network space. Let's cancel this because I don't want to make any changes there. So that gives it the let me zoom in a little bit, make that better. All right, so that gives it access from my desktop to the VLAN 200 network space, and then that's the address that gets assigned, which is the .2 one. Okay. Now I'll show that here in a little bit how I configured it on my desktop, but that's how you configure it on the port for the switch. Okay. Now I have to do kind of like the same thing for all 3 Raspberry Pis. So the Raspberry Pis are connected on port 22, 23, and 24 on the switch itself. You can see them right here, these 3 right here, and you'll see that the port profile that is set for them is the Lab Pi access. So they don't have access to the default LAN or anything else. They're in an isolated network. And they only have access to the public and within its network space. So that was kind of like figuring that out, and then assigning the appropriate port. Okay, so the node 1 has the .10, node 2 has .11, and node 3 has .12. So that's how you can assign these 3 devices on these 3 ports, the VLAN. And then once you do that, then I have to do some configuration. So this is just like pre-network one-time configuration on the router and on the switch. Okay, now I actually have to configure my actual host. So like the desktop that where I'm recording from has to have an IP assigned to be able to be able to talk into that network space. So from and on my Ubuntu 24.04 desktop, I'm using Netplan, and with Netplan I have this section for the zero indexed network port on the quad port card to basically use the 192.168.200.2 network space. So that's essentially how I can how I configured my my desktop to be able to talk to that VLAN. So I can actually do an app like this, and then you'll see it here. It's configured, it's up, and then you'll see here's the address, and you can tell that it is actually connected to the switch. So you can see that there. Now, so here there was a little bit of trouble that I was having, and basically it was due to the two different port profiles. So you need to have the trunk one and then the access one, and so after figuring that out with the help of my AI assistant, then I went ahead and I was able to ping the gateway. So from here I can show that I can ping the gateway. So that's the actual me pinging the gateway itself. And then the actual Raspberry Pi devices I've already bootstrapped them, right? And we'll show that here in a minute. So I want to show you that I actually have network access to each of the 3 Raspberry Pis. That's the .12 and the .11. So I do have access to all 3 of them. I'm going to SSH into the first one, and just a bit of prior knowledge. When I was developing all this work, I was kind of like rinsing and repeating a lot of different fixes. So I did some changes to cloud-init, and I ended up like reflashing the first Raspberry Pi at least 5 times as I was playing around with cloud-init and figuring out how to do it properly. Eventually I landed on a base configuration. I went ahead and I flashed the second Raspberry Pi, did some minor changes to that cloud-init configuration, rinse and repeat, and then I did the third one, which is the final kind of configuration that I have. So here I'm just showing that I can connect to the first one. I'm going to connect to the second one. You can see that I can connect the SSH to the second one, and then I'm going to connect to the third and final one. This is essentially the third one, and there I can elevate. I have sudo-less password on this one. Again, remember you cannot. If you try to, if you try, this should be disabled, but I shouldn't be able to SSH to it won't let me SSH to the device via root. You need to be the admin user. And it doesn't allow like password based login, only SSH based. So now that I'm SSH'd here into the Raspberry Pi, I want to just like show like, hey, this is cloud-init, and I think it's like status -- long, and you can see right, it's done. I wouldn't worry about like this decreated stuff. It's just complaining about this warning, which is not really that much of an issue. But cloud-init did run, it did complete, it did everything I asked it to, which wasn't very much, it wasn't a lot of work that it did, but you can see that it ran, and the logs for cloud-init, you can actually see them here. There's 2 of them. There's this cloud-init log, and then the output itself. So that's pretty much the extent of how I can how I verified cloud-init was running and not. There were some issues where I accidentally, at the beginning when I was working on the very first Raspberry Pi, where I actually connected it into the incorrect port on the switch, and so it was just, like face palming myself here, like, why did I do that? So I had to kind of like unplug it, connect to the proper port, and actually I had to refresh the NVMe so that it could redo the cloud-init. So that's pretty much the kind of like the demo that I wanted to show. Now, in summary, I covered some of this, some of these things, but there were some specific issues that that came up, and kind of like this is somewhat of a minor list of that. So like the VLAN port profile mismatch that I mentioned before, where initially, actually I didn't call this out, but initially I didn't know that I needed to do 2-port profiles for the VLAN, right? So one for the actual dedicated network space, and then another one to allow external access internally. So from the default LAN to the VLAN 200 network space. I didn't know I needed that, and so with the help with my AI assistant, I was able to figure that out. The cloud-init section, this one I didn't mention, right? There's multiple iterations that I had of this process, and the final one landed on the third node. Either way, they're all bootstrapped. They have everything that they need. It was just some minor fixes here and there over time. As part of that, it surfaced some of the swap issues that I discovered, and then the next issue on the list about the NTP ordering, where the Raspberry Pis don't have a real-time clock, so you have to kind of like do that hack where you do the synchronization of the time before you can do like any sort of apt package work. The next one was the fact that Debian Trixie for the Raspberry Pis don't support Netplan. At least that's what the AI assistant told me. I never really kind of tested it. Well, actually, I did test this. So I actually did try to put the network configuration within the user data for cloud-init, but that didn't work. So I had to go with the network-config file for cloud-init, and that does work. That does set up the network on the Raspberry Pi. The last one isn't necessarily a problem, more so just a summary that I had, that kind of bake.sh script that does the initial massaging of the image on a copied one, right? So in summary, that's all that I did, and some of the issues I had. So I hope this is useful for someone. That I'll have a separate project where I'll actually go in and figure out how to deploy Kubernetes to the Raspberry Pi cluster within this VLAN network space. And I might even try figuring out if I can do any sort of like caching for like images and packages. I actually did figure that out, how to do that for my virtual machines, but I haven't actually done it for like real hardware, in this case the Raspberry Pis. Maybe I might do that, we'll see. Anyway, so that's all I had. I hope you guys learned something, so take care, bye.